right, welcome to this explainer. You know, we look up at the night sky and it looks pretty static, right? But how do we actually know what happened out there billions of years ago? Well, today, we're basically going to play cosmic detective. We're going to look at how astronomers use some really specific, observable traits of stars as literal clues to unlock the crazy, complex history of our very own galaxy. We are treating the night sky like a giant historical scene. And by the end of this, you're going to see exactly how the universe leaves its fingerprints everywhere.
So that brings us to a massive question. How do we actually uncover the galaxy's past? I mean, think about it for a second. It's not like we have a time machine to just hop back 10 billion years and watch the Milky Way come together. We can't rewind the tape to see how all these stars ended up where they are. All we've got is right now, literally just the light hitting our telescopes tonight. So how on earth do we piece together all those epic collisions and formations from so long ago? Well, we have to look for some very specific evidence hiding right there in the dark.
And it really comes down to looking closely at two major forensic clues locked inside the stars themselves: their motion and their chemistry. It sounds simple, right? But these two factors are the ultimate astronomical fingerprints. By tracking exactly how a star moves through space, its trajectory, its speed, and by breaking down its exact chemical makeup, astronomers can actually reconstruct its history. It's wild. A star's motion and its chemistry tell a story that survives totally intact for billions of years, just waiting for us to read it. Which brings us to our primary suspects for this explainer, a super specific class of celestial objects we call halo stars. Now, halo stars act as our direct window into the ancient universe because of a few dead giveaways. They are incredibly old, they are what astronomers call metal poor, and they have these wildly unusual orbits compared to the vast majority of stars we see. And honestly, it's exactly because they're so weird and so out of place that they're so important to us. They literally carry the galaxy's secrets right inside them. Okay, let's zoom in on those chemical clues for a second. We're looking at three traits that are completely intertwined here: old age, being metal poor, and having low metallicity. Think of a star's chemistry like its birth certificate. Because halo stars are just so insanely old, they formed way back before the universe had a chance to get saturated with heavier metals. So, when astronomers spot a halo star with low metallicity, they aren't just seeing some random chemical quirk. They're looking at a pristine relic. That metal-poor makeup is a direct indicator of extreme ancient age. Which, of course, naturally begs the question, if these things are so remarkably old and their chemical makeup is so drastically different from the stars in our regular neighborhood, where did these metal-poor oddballs actually come from? Like, how did they end up here, swirling around our galaxy with these bizarre traits? Well, to figure that out, astronomers had to develop theories that perfectly matched both the motion and the chemistry clues we were just talking about. And that gives us two main origin theories for these fascinating objects. The first possibility is pretty straightforward. Maybe they just formed super early in the universe, right alongside the initial birth of the galaxy itself, which preserved that pristine metal-poor chemistry. But the second theory, well, this is where things get incredibly dramatic. The evidence strongly suggests they could have been brought in by smaller galaxies that violently merged with our main galaxy later on. I mean, just picture that. Entire populations of stars acting as ancient immigrants, violently pulled in by gravity during massive cosmic collisions, forever stuck in these chaotic orbits from the sheer trauma of their arrival. To really appreciate how unique they are, you kind of have to contrast them with the norm. On one side, you have our halo stars, totally chaotic, unusual orbits, super low metallicity. But then on the other side, you have disk stars. Disk stars make up the flat, spinning plane of the galaxy. They're orderly, they follow the traffic laws, so to speak. And crucially, they are way richer in metals. They formed much later out of the recycled material of older stars, so their chemistry is completely different. It's this massive contrast between the orderly, metal-rich, modern neighborhood and the chaotic, metal-poor, ancient relics. When you actually map these traits out side by side, The dividing line is just impossible to ignore. Under motion, halo stars are doing their own unusual thing, while disk stars are perfectly orderly. Under chemistry, halo stars are metal poor and disk stars are metal rich. Simple as that. By comparing these properties directly, it creates this perfect, clean dividing line that separates the wild, violent ancient history of the galaxy from its much more settled recent evolution.
So, why does this all matter? Well, it matters because these stars are the ultimate breadcrumbs for galactic evolution. The messy, chaotic history of our main galaxy isn't lost at all. It's literally preserved perfectly in these exact differences we've been exploring today. Every weird orbit, every single trace of low metallicity in a halo star is a surviving piece of a billion-year-old puzzle. By tracking how they move and decoding their chemistry, astronomers aren't just staring at pretty lights in the sky, they're actually reading the historical record of how our galaxy was built, piece by piece, merger by merger. I want to leave you with this one final thought. The next time you step outside and look up at the night sky, realize that you are not looking at a static painting. You are looking at a living, breathing history book. Every single point of light has a backstory. So you've got to ask yourself, is the star you're looking at right now a well-behaved, orderly neighbor that formed right here in the disk? Or are you locking eyes with an ancient immigrant, a metal-poor survivor from some tiny galaxy that smashed into ours at the absolute dawn of time? The clues are all right up there, just waiting to be read. Thank you so much for joining me for this explainer, and hey, keep looking up.